So today we're going to talk about perpendicular bisectors. Think about that name for a second. Perpendicular, intersecting, make 90-degree angles, and bisector, cutting into two equal parts. So we got a lot of definitions here that are going to come up, and that's your bell, that are going to come up from time to time. Perpendicular bisector, you can read that, equidistant. All these definitions are definitions that you need to know. As far as today's lesson, I'm not going to spend a whole bunch of time on all of these, maybe these two here today, but these are things that we will come back to, so make sure you get these things down in your notes. So if you need to pause it to write them down, go ahead. Alright, the first thing we need to talk about is this theorem for the perpendicular bisector. It says in a plane, basically on a sheet of paper, if a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what is equidistant? A point is equidistant from two figures if the point is the same distance from each figure. So equal distance is kind of what's in there. This is basically saying in plain English that this point is on a perpendicular bisector, because I know it's a bisector because AP and PB are the same. Look at those marks. It's perpendicular because of this box. If a point C is on that line, then CA and CB are going to be the same. As you slide up and down this line, it's going to be an equal distance for AC and BC. It also means if CP is a perpendicular, that's what that means, bisector of AB, then CA equals CB is what that says. And notice that if it's a bisector, that PB and AP are going to be the same. So based on this, let's look at this example here. AC is a perpendicular bisector of BD. So we know that this is a perpendicular bisector. They told us that. Find AD. So they want us to find this length AD here. So how am I going to find that length AD? Well, I have to be based on this relationship here. What relationship? Well, since this is a perpendicular bisector, then AB and AD are equidistant, or in other words, 7x minus 6 equals 4x. And so that would be the equation that we would use in order to solve the problem. 7x minus 6 equals 4x. So that's what I would do. 7x minus 6 equals 4x and solve 4x. Subtracting 3x from both, 7x from both sides. You get negative 6 equals negative 3x. Divide by negative 3 and x equals 2. That's not your answer. That's just telling you what x is. So if I put 2 in right here, then AD would be 8. I'm doing that with the mouse, so if it sucks, oh well. Alright, so how do I know to set those equal to each other? Because of this theorem here that tells me CA and CB are equal to each other. Alright, here's another example. In this diagram, KN is the perpendicular bisector, so we know that KN is a perpendicular bisector of JL. What segment lengths in the diagram are equal? So what things do we know are the same? Well, we know JM and ML are equal because we got those numbers there. Plus, that's a perpendicular bisector. But also, if this is a perpendicular bisector, then JN is congruent to NL, right? And also, JK is congruent to KL. So, not only are these two sides with the 13s congruent, but JN, because this bisects JL. This line right here bisects or cuts into two equal parts, JN and L. Alright? And we know that those are going to be equidistant just like those sides right there. Pretty simple so far. The last thing I want to show you is concurrency of perpendicular bisectors. Alright? So the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of a triangle. So let's go back here for a second. Concurrent, when 3 or more lines, rays, or segments intersect at the same point, they are called concurrent. Alright, so back to this. This point is concurrent because you got several lines intersecting more than 3, or at least 3. So what you have here is if PD, PE, and PF, so PD, PE, and PF are perpendicular bisectors, so these are what we just been talking about all day, perpendicular bisectors, then PA, PB, and PC are equal to each other, and those are the distances to the vertices. And so that'll come up later, but this is something that we need to know. The focus of today is working with these, okay? So that's what I'm going to do. Okay guys, so I was just talking and talking and I must have paused it. So let me go back and show you what I did. I was talking about how the theorem that we were working on, this one here, was the most important for today, even after I showed you this one here. And I don't know how much of this you caught, but we're not going to focus on that one much today. It will be this one here. And so I went through, and you didn't get to see it, but I worked through these examples, and so I can just describe what happened here. In these examples here, I know that this is a perpendicular bisector based on the setup. Those two are congruent, those two are congruent, and that's a 90-degree angle. So in order to find CD like they wanted me to find up here, I took these two and set them equal to one another. Did my algebra, solve for x, which is not my answer. I had to put 1 back in for x here for CD, and I found out that CD was 6. So it's all based on how you set up your problem. And how you set up your problem here is that the sides or the segments will be equal to one another. And so I did it again here, and I was able to find out again that x was 1, and CD in this particular problem was going to be 4. And as I move down the picture here of the page, you can see that the pictures kind of got a little bit more complex. But again, this side equaled that side, and so I did my algebra on this one, and on the next one here I kind of did all of it on one line, subtracting and adding and stuff like that, just so I can have the space or whatever. But I found out that x equals 8 on number 3. Substituting it in, you'll find out that CD will be 20, and here x was 3 after you set those two equal to one another, and CD was 26. So as I was working through that, you guys missed it all. I guess I paused it. I clicked something to pause it. If there's an issue with something, let me know in class and we'll try to figure it out. But this is how you would use that theorem there. Hopefully this made some sense, and if not, it's your fault. No, I'm just kidding. Let me know and I'll see what I can do to help. All right.